So welcome everyone. Thank you very much for coming. I'm very happy to have here with us Isabella Masina and Giuseppe Presti for a lecture, 3 days lecture series on the physics of music. So Isabella Masina is a physicist, theoretical physicist, working on particle physics, cosmology, and recently on music. And she's teaching a PhD. A course on music and physics, and Giuseppe is a veteran of the CERN IT department, working on CERN storage systems for almost 20 years, and they're both also musicians and passionate about music. So I'm very happy to hear their lectures. So, the floor is yours.
Thanks. Thank you for being here. We are delighted, surprised to see so many people, friends and colleagues. And the origin of this kind of lectures is actually, as Giacomo said, this course about physics, music, acoustics that I gave with many other colleagues helping me at the University of Ferrara, which is still ongoing. So, you know, acoustics is so multidisciplinary, and that you really need contribution from many people, from theoretical physics in the sense of mathematical modeling, neuroscience, acoustics also for architecture, digital signal processing. So my preferred engineer is here, and he contributed with the Python simulations and computational tools to the course. So, as said, physics of music is so vast issue, and we tried to select the topics that we like most. We find them interesting for us, and we hope for you too. And we tried to add some original touch, especially for the issue of consonance and dissonance. And you see, the presentation is based on our scientific backgrounds and skills, so I will play the role of myself as a theoretical physicist and Giuseppe as an expert of computing. So thank you again for being here, and let's start. So these are the questions that we try to give an answer, or to increase your curiosity, your awareness, and to possibly give rise to many other questions. First, what are the physical foundations of Western music, in the sense, is consonance and dissonance something physical or just more subjective? Is there something objective or subjective? How the cultural features are important? Or there are some, let's say, features in the signal that we hear that can tell us about some objective properties of consonance and dissonance. I think that everybody asked himself this question. Now, then, why are there 12 notes inside an octave or not 13? I mean, 12, you know, are the chromatic notes in one octave. The black, if you add the white and black, it's 12. The white in one octave are just 7. If you add 5, the black, you have 12. So why? Is there some reason, historical, cultural, physical reason for this? Why is the equal temperament so successful? The equal temperament, you probably know, is the temperament that we use nowadays. But there have been historical temperaments that are different. And what about microtones, if you want to be a little bit modern, but as we will see, it's quite an old idea of this, of the microtones. So we will try to answer these and other questions that for sure might have come to the mind of scientists playing some instrument. And actually many of us, I imagine, play a bit or are interested in music. And so at the end of the series, we hope that we will have more questions than before. This is the goal. So we start from our detector, which is the ear. A few comments about the ear. Then the case study is the vibrating string and Fourier analysis. As an harpist, I have to start with some plucked string. Then psychoacoustic. We need some notion about roughness, beatings, and so on in order to deal with the consonance and dissonance. And today we will show you some tests we made about intervals, so dyads, two sounds played simultaneously. And some of you were involved in this test, so we are happy to show you the result. So the ear functions as a Fourier analysis device. And for us, it's so nice. So Ohm was not just related to something about electricity, but he also did the law of hearing. The perception of the tone of a sound is a function of the frequencies and amplitudes of the harmonics, not of the phase relationship between them. So, if you have some signal which is associated to pressure waves in air, anyway, it is some signal which is in the time domain, the ear actually does a short Fourier transform in the frequency domain. This is just to remind what the Fourier transform is if you don't work with the Fourier transform every day. Here is the definition. You take some signal of time and you go in the frequency domain, and typically you study the power spectral density, which is the modulus square of this SF. So this is some sort of autocorrelation. Good, but let's go to the short time Fourier transform, which is what our ear actually is doing, because there is some windowing function, typically take a Gaussian, and for the ear, the width is about 0.05 second. So the ear does some sort of short Fourier transform. So we have a spectrogram defined as the modulus square of this short time Fourier transform, and nowadays it is possible to have the spectrogram also from the smartphone. It's very, very familiar. I will not comment on the theories of hearing. There is one interesting theory, the place theory of hearing, which correlates the pitch to the position along the basilar membrane. And this is a part of the knowledge about the function of the hearing system, which is anyway still today under study, because there are also non-linearities which are very important. And you know, we give just this kind of paper as an example. The ear beats the uncertainty principle associated to time and frequency. So this is quite impressive, even better than the uncertainty principle. So non-linearities are important, but we, of course, not are going to comment on the functioning of the ear. We rather stay on the signal as a function of time. So, you know, we are able to establish the pitch of the sound if its harmonics or partial, if constituents, frequencies are harmonic. Namely, if there is some fundamental frequency of the tone and the other frequencies which compose the sound are proportional, are equal to n, where n is some integer time the fundamental frequency. So this is a harmonic sound, and it sounds nicely. Otherwise, if there is not such a dependence on an integer n, you you hear something which might be a noise or rumor. This, on the contrary, is a harmonic sound, some musical sound, let's say. So the question is a vibrating string harmonic? What are the amplitudes and the frequencies associated to the signal in the time domain which is produced by a string, a vibrating string? So now I will discuss these kind of amplitudes and frequencies, and I will show you that, of course, they are harmonic. So take this vibrating string with fixed endpoints from 0 to L. This is the length of the string. Take this displacement F, so it is the highness of this curve. And of course, the displacement, one can show, satisfies the D'Alembert wave equation in the approximation of small displacement and blah, blah. This is the D'Alembert wave equation that you might remember from your studies. And V is the velocity of propagation of the sound of the wave in the string, and it depends on the tension and the linear mass density of the string. But let's go on. This is the general solution. The general solution depends on Fn, which are actually proportional to n, where n is integer. But let's go fast, because I see you are a bit tired. What the ear detects is the short Fourier transform of the pressure wave generated in air. And this signal can be written in this way: some coefficient times this sign with Fn, the frequencies that I show. And so the amplitudes can be calculated by specifying boundary conditions, while this Fn is harmonic. So we are very happy, it's harmonic, and you can visualize all the harmonics in the way you know very well. Let's go on. Let's take something, let's say, more specific. Let's take a plucked string. So you start at time equal to 0 with a sort of triangular form, 0 velocity. And so you have the boundary conditions that allow you to calculate these coefficients, these amplitudes. Let's do it. I did it. So those vanish while the other are given by this kind of formula, which depends on h, how much you pull, and L divided by K. So L is the length of the string, and K represents where you pluck the string. If you have K equal to 2, you are in the middle. If you have K large, you are close to one end. So you see the amplitudes depend on K in this way. And you can identify some, you can look at the dependence on n. So there is 1 over n squared sine n pi over k. So this is sort of C1 where n is equal to 1, and you study this essentially. So where do you pluck your string usually? In the middle or close to the end? Guitar. You play guitar then, possibly. So here are the coefficients for guitar. Let's say guitar-like, k equal 20. And these are the coefficients if you are more an harpist, trying to pluck the string in the middle. And you see also, it doesn't work. The animation, it stopped. The animation of the string, anyway, it stopped. Anyway, now, this was the, let's say, theoretical introduction. And we obtained this nice formula, elegant formula for the coefficients. And now we ask the engineer to let it work.
Okay, so let's give it a try. So this is, just to a bit play on combining together indeed. So we have this, this derivation of those coefficients. This is an easy formula. So what can we do? We just put it into Python. We use our common tools that I know many of you already know, but I will give a mini detail on that. But it's very straightforward to actually generate a waveform with Python. So we decide we take a frequency. So take the central C or Do in a piano keyboard. For the moment, let's play the harp. So to please my colleague here, and so K equals 2, and we generate the waveform. So the waveform then looks like something of this kind, where we have on the left the waveform of the time domain, and on the right the power spectrum that already tells that indeed the partials, it looks kind of okay in the sense that the partials are going down, and indeed we see that here we have this coefficient 1 over n square, so we expect the partials to go down. So let's play the sound, and this is supposed to be a plucked string, but well, it's not really fading away, right?
It's fantastic. It's very elegant formula, very elegant sound. No, the only problem is that the D'Alembert equation is associated to energy conservation. And if we are in the real world, we have to introduce some friction. So let's put a damping factor. So the higher is the harmonic, the sooner it vanishes, and take order 1, second, because this is our scale, and propose to the engineer to implement this.
Okay, all right. So then we put this extra damping, which, okay, easy to put in such a context. And what happens? Okay, now sounds good. We have a sound of a harp kind of instrument, and we see also what we call the spectrogram. So how to read this, if you have never seen this kind of plots, this is like a 3D plot, if you want. So this is time, this is frequency, and it's really like you make several Fourier transforms part by part over time, and then you see indeed the transition, and you see indeed the partials that fade at different time, because the higher partials will fade rather quickly. So that's how you would represent it and then we can play with the guitar. So the guitar then becomes this, which you see that the sound is different, right? We have I can try and So here we have a kind of more metallic sound, and in fact the reality is that we get many more partials, and they are also a little bit more extended. So then we have at least kind of the tools to play, to generate sounds, to play music, but you see that here we are kind of cheating on one important aspect for people that play an instrument. We are generating the stimulus. This is very important. We are really just abstracting, okay, at least we went to real world by putting the damping, and the sound at least looks really like, or sounds really like a string, but we are dropping the resonances of the harmonic structure of an instrument. Why that? Because we want to really study the sound in the sense of the purest possible sound, without all of the extra distortions or contributions that are made by the instrument itself. So this is kind of indeed, it's kind of the abstracted sound, which then you can multiply by the transfer function of the instrument, and then you generate the sound of an instrument, in fact. But yeah, this is like the stimulus. So all right, we have seen a little bit how to generate things, and now just to have more an idea. So all of this, actually, apart the joke between us, this is also something that we did with the students. So this was part of the course we did, where the idea was really to reuse tools that are very common, and I'm pretty sure most of you know about those tools, NumPy, Matplotlib, and etc., which are very common in data science. So it was a matter of developing some Python notebooks, so with IPython, to actually be able to do all of these kind of simulations. And we are going to use that through this series. The interesting bit is that it's very easy to actually generate those three kind of plots that we've seen. So the waveform in the time domain, the global power spectral density, and also the spectrogram. So the power spectral density time by time, so chunk by chunk, if we can say. And we will see that the three of them give different information, and it's not obvious to only select one. Let's say the spectrum is most complete, but it doesn't tell the full truth, as we will see. So then, what do we do now? We have another case which we could also study, which is also useful in this kind of analysis. That is, what happens if actually you don't do any fading. So you have an instrument which is featured with some kind of sustained stimulus. Think about, you have the voice itself. When you sing, you are singing in a constant at a constant dynamic. Strings also work like this because you are stretching your chords this way. Pipes, all of those instruments, they all work the same way. So in this case, what happens? Okay, we don't have any damping, and okay, one example we can make is actually something of this kind, which is quite typical in pipes, where if you're not accustomed to Python, this only means that I want to damp the even harmonics, so when this is 0, faster than the odd ones. So I'm kind of selecting them. And you see that in the power spectrum, some harmonics are higher, some others are less high. And the sound is a bit like indeed a pipe or like I can make it maybe play again. Yeah, looks really like a pipe or a trumpet or something like this. Again, there are no resonances, right? So this is just the stimulus. So of course, then all of the instruments, they put their own timbre, and that's where they make a difference. But it's useful to have this as a kind of sampling sound which contains harmonics, because in the end of the day, we are going to always play with harmonics. There is never a case of a single frequency, pretty much. Okay, so now that we have, so these are really the very, very basic tools to start doing analysis of sounds. And what we want to do, and this was already a bit introduced by Isabella, is actually trying to study what happens when we combine sounds of different frequencies. So the typical thing is, okay, we have two frequencies, F1 and F2, and we try and see what happens together when they go together. First thing, this, I guess everybody did this experiment, is the beating that you have when the two sounds are very, very close in frequency. Right? I mean, this is the very classic wah-wah-wah effect that we all know. But that's not the full story. There are many other things. Typically, what happens when the two frequencies are close but not that close, and we have to define what this close or very close means, of course. And we will see that we hear what we would call roughness. So the two sounds are actually kind of fighting, and the composed sound is a kind of complex sound which gives this perception of roughness. Then we can get more far away with frequencies, and then at that point you get less, the sounds are less rough. And then it also happens that when you cross some specific points, so around some specific points where the two frequencies are actually, the ratio is simple, and we have to define what simple means, we have what we would call islands of consonance. I mean, the sound becomes a little bit consonant, but also what happens around it, so when the frequency is not exactly that, there could be some, there are some interesting effects there. And, well, this looks like this is related to the waveform that becomes simpler, but we have to see what this happens. And we have also this effect of what we call the secondary beatings. So there are beatings also when the two frequencies are not very close. They are very far away, but they are close to this kind of ratio. And this we can have the clear perception of those. So now we have to define what all that means, because otherwise we're just talking about, we have to measure. So we want to measure things. I mean, the whole spirit here is to play the role of, we are scientists, we are physicists, we want to measure those effects, even though there are many subjective parts in the perception. So this is what we call psychoacoustic. So we are going to introduce two definitions. One is called the critical bandwidth, another one is called the discrimination limen. And the two definitions read something like this. So the critical bandwidth is actually a band, so it's a range of frequencies, within which the two sounds actually are interfering in a way that the perception is actually rough. So, of course, the definition goes into perception. So this is a psychoacoustic definition. It's not completely pure physics. The discrimination Limen is something else. It's about the difference of frequency that we can perceive, that we are able to notice, in fact, between two different sounds. And it is important when they are heard separately. And this depends on the difference. It also depends mainly on the dynamic, on the volume. If you are whispering, it's more difficult to really make a difference, but if they are loud and they are actually in a nice range of frequencies, then we have a very good resolution there. And all of those things have been studied in the past, actually not even so much in the past, but these are more or less the numbers if you take indeed like the central C in the keyboard. So the central C in the keyboard is 262 Hertz, and the critical bandwidth is about 100 Hertz. And we are going to see that actually we can hear beating until about 10, 12 Hertz, so in a frequency difference of about 12 Hertz maximum. Then the sound is rough, and then the two sounds are really clearly separated. And in fact, what has been studied, this is actually taken from a paper by Zwicker and other people, not even that old after all, where we see they actually did tests with people to measure this effect. So the important one is this line. So you see that for high frequencies, the width of this critical bandwidth actually goes more or less linearly with the frequency, which is kind of, okay, if you think about it, it's like, if you take those lines, those correspond for people that know music, but even for people that don't, it will be clear in the next lectures as well. This is the interval of what we call a major third, the big M3. This is the minor third, this is the major tone, or a tone, and this is the semitone. So here what we are saying essentially is that a tone or a semitone, they always fall into the critical bandwidth, and they sound dissonant. And above that, they do not sound so dissonant. Actually, they sound quite okay. But if you go low in frequency, and so here this means going really low to the left hand side of the piano keyboard, then it kind of flattens, which means that actually all of those intervals become dissonant. And okay, as a pianist, I know very well that if I play the bass, I can only play octaves. I cannot play a full chord because it's just a lot of noise, right? I mean, there's a lot of dissonance that is added with a full chord played very low on like around here, while the octave is still okay. I mean, they are distant enough. If people that play know this by heart, let's say, they don't even need to realize. I mean, it becomes obvious. But it's interesting that it actually depends on the fact that then we have this flattening of the critical band. And actually, the interesting line is more this one, because this is really the limit, but this is really when they say, okay, now the two sounds are completely separated. But this line is more where we have the worst effect in terms of dissonance. And otherwise, much lower is the discrimination Limen. So this is actually, this means that actually we're able to distinguish, we are able to distinguish two sounds which are very, very close, actually. Like a few hertz are easy to distinguish. We are quite sensitive there. I mean, the ear is making, well, the brain is making quite a lot of effort there. All right, so with all this, then what we can do is really try and play this, trying to see these effects by our own ears. So we are going to simulate a very classic signal that is a chirp, a sweeping frequencies. So we'll take F1 fixed at 256 Hertz. This is because I'm an engineer and I love power of twos, nothing else than that. And then I have an F2 which sweeps from a little bit below F1 to a little bit above 2 times F1, which in musical terms, it means that we get then this kind of plot, but it means that it's like an octave, what we call the octave. And also to account for how the ear is perceiving sounds, we actually make the sweep go logarithmic, which is trivial because Python, I mean, I don't have to do anything. This is SciPy, it's a very well-known package for signal processing, and they provide a nice chirp function that generates this waveform. So what are we looking for? We are looking for beatings when we are very, very close to the two frequencies are very, very close, and then roughness at the beginning when the two frequencies are still near, and then the two sounds that become separated. And this is how the sound would look like altogether. And so here we see the waveform, even if it's very compact, we can still see some features that are interesting. And on the bottom, this is the spectrogram. So we see F1 that is constant all the time, and F2 that goes linear, well, on a log scale. So it's linear, it's actually exponential. But for us, for the perspective of how we perceive the sound, it's actually linear. So it's a linear sweep of the frequency. Some interesting points in this plot are actually what we call the unison, where the two frequencies are actually really overlapping, which is this line. Then we have what we call the octave, so the ratio. Oops. Did we get it out of charge, or looks like I have to go? Or is it like we got? Interesting. Even the keyboard doesn't switch. Looks like either the slide got stuck or no, but the mouse is there. Huh? Then if I do this, that works actually. Well, look, I can use my mouse. Then it's no. Okay. Anyway, the mouse is good enough. not a big deal. So I wanted to, because then I have anyway the arrow. So it's actually, well, it's not as nice as the green dot, but it's good enough. So the important parts that I wanted to kind of make prominent is so the unison we mentioned. Then what we call the octave, when we have a ratio that is 2 to 1, that is this point, and you already see that the waveform is a bit strange. It's not completely like random as it is elsewhere. Then we have also this other point that we will see in a moment, which is where we cross the ratio of 3 to 2, which is a kind of simple ratio in that context we mentioned. And then to report what we just discussed. So this is the place of where we cross the maximum roughness, and this is the limit, what we call the critical bandwidth limit, which means that past this point, the two sounds must be felt completely separated. And before this point, of course, the transition is very smooth. It's not like completely sharp. But especially around this point, we must perceive the two sounds very, very much messing each other up, if I can say. So let's play the sound and let's see how this works. Okay, even better than when we played it at home, because at home we have a very bad audio system. Here it's working actually pretty okay. I mean, in the sense of, now the mic is even too high because I have to lower a little bit. Yeah, I raised the volume to really play the, like, I guess you could hear at least, okay, easy, the beatings, the initial beatings, these are the beatings that everybody knows. And we can even see them in the spectrogram, because the spectrogram is really looking after what the ear is. I mean, we go with a very short time window, so that it really matches what the ear is perceiving. But then, did you hear the beating at the octave? I'm pretty sure everyone heard some beating there, like some. And did you also hear around this point? It was clear to me. I knew that what to look for. Was okay. And even in a few other points, around there and around there were also some beatings. And this is not random. There is a very physical reason for that. So then we can explore a little bit more what we mean by these kind of beatings. And typically, the important one that we see near the octave is actually now generated here. So the idea here would be to have the two frequencies that are almost one, the second one twice the first one, but not quite. So a little bit out of tune, we would say, in musical terms. So what happens in this case? So here the beating is even stronger. Why? Because I've added also harmonics. So this is like the sound we had before. And the beatings pattern is actually very clear in the spectrogram, right? So this is basically the second harmonic of the F1 that is beating with the first harmonic of the F2. Because the two are almost overlapping, but not quite. And same here, and same there, etc., etc. But the beating is still there also without that. Right? You can hear that there is a bit of whoa, 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 right? So this kind of sound is actually beating because of this mistuning. So this is what we call the mistuned octave. And this is actually one of the cases where you see beating on the waveform. You don't see it in the spectrogram. You don't see it in the power spectrum because the two frequencies are in a way far away. So here, in a way, our ear apparatus is actually feeling this is the envelope of the signal, not just the signal itself, but the envelope itself. So, and there is this kind of modulation in the amplitude that comes from the envelope. So that's where I say the spectrogram tells a lot of things, but not the entire truth. And the same thing we can actually play with the fifth, what we call the fifth. And okay, those names, octave, fifth, third, etc. We will see them tomorrow, and there will be more. It will be more clear why they are called also that way. But for now, this is actually the way we name those intervals, those ranges in music. This is the standard way. People that know how to play, they know fifth since ever. Maybe they never asked why they are called fifth, but. So a fifth, when it's perfect in tune, it looks like or sounds like this. Okay, so far so good. Then I can make it out of tune by having the second frequency a little bit, not exactly 3 out of 2. And there you see very nicely the slow beating that actually goes at 2 Hertz. So it goes twice the difference in this case. And yeah, this is kind of, we have the same consideration as this we call it mistuned fifth, and it's similar to the mistuned octave. So when there is a mistuning, it's actually very, the ear is very sensitive to this because we have these beatings. And it's impressive that 1 Hertz is enough to hear the beating. And this is actually the core reason why musical instruments are tuned by beatings, by fifth, by octaves, and by the beating that we generate when they are not in tune. Because we really exercise this spatial sensitivity of the ear. This is even more than the sensitivity we would have by the discrimination limen. If we would get the two sounds separated, not together, no way to see the difference. You can play an out-of-tune instrument. If you play the single tones all separated, it's a little bit hard to detect that the instrument is out of tune. But if you play a chord, then you strike it. You get it immediately if it is out of tune. So this aspect is actually quite relevant, the beatings that we get there. Are we done? Not yet. There is one more. Wait, yes. I forgot that we have also did the same effect with harmonics, which is what we play normally with instruments. Of course, the effect is even reinforced because we have the higher harmonics that really beat. No? So we have the beating pattern here, there, etc. I make it. Let me go back if I can. Yeah, so that. Well, you have again this effect of trembling, let's say, So all of this to say that we know we have this effect. It is actually quite important because it's really a physical effect. We see properties of the signal, typically the envelope, that really make it a physical effect. And we know that this can be exploited. I mean, it makes sense for the analysis that we want to do afterwards. I was saying, are we done yet? We have another effect that we also want to exploit. That is actually about what, again, in music is called the fundamental bass, or the missing fundamental. So now we go and play with two sounds where we know that they are in, it is again a simple ratio. We assume that the ratio is m over n, where m and n are coprime, meaning there are no common factors. So 3 to 2 is perfect, is a good... and we define a new frequency, which is this one. So in the case of the fifth, it would be half of the F1, or a third of F2, if you think about the fifth, as we did a moment ago. So this is a completely different frequency. This frequency is actually is known in many ways in musical papers or discussions. It's also called common bass, or typically it's called missing fundamental, because it is actually, if you play several of those frequencies, it really looks like it's the fundamental of the whole sound that is missing, and in the time domain it is actually the period of the waveform. So there is a very direct representation of this in the time domain. So now the thing is, this sound does not exist. It's a virtual sound, right? We are defining it, but when we play the two sounds, that does not exist. So can we actually detect it? Yes, we can, by again exploiting our sensitivity to beatings. So the trick I'm going to do now is that I play again the P5, so the perfect fifth, perfectly in tune, and I add on top this F0, but I make it mistuned. So I actually add the twice to the common bass. And you already see by the waveform that actually the amplitude is modulated. So there is actually a modulation effect, which is physical. Now this is also very debated, because we read in many papers that this effect is mostly kind of at the neural level, like the brain is synthesizing the extra sound and then it creates this kind of beating effect, etc. But we are kind of challenging this by, look at the waveform. To me, this is very physical. There is there is a clear modulation of amplitude. And okay, right, you cannot see it in the spectrum nor in the power spectrum. There you have the difference. So this is F1, this is F2, and this is F0. That is half of F1. So there you have it as well. And by the sound, okay, I'll maybe raise again a little bit the volume. It's very tricky to detect, and I would even suggest you to try. I will probably put at least the sounds available so that on the earphones you can get them. But especially if you concentrate on the lower sound, there is a bit of wow effect. It's very subtle, but it is actually. I can try again if you like, just to have. Really try to focus on the lower sound more than on the higher sound, and then you see the effect. It goes a bit like in order of indeed of 2 hertz. This kind of it's very subtle, but it works. It's really there. So we have something related to this. And by the way, we talked before about nonlinearities. People that play the instruments, they also know that nonlinearities play a role. And in this case, there is an interesting kind of coincidence that the combination tone that is called the Tartini sound, if people know about Tartini, this is actually a violinist, and he described this third sound as actually the difference between the two. And this is something that you can hear when you are playing your violin and you have it really close to your ear. So or with some headphones, but you have to push a little bit your audio system, and you have to go loud so that you trigger the non-linearity of your ears. So at this point, this is really in your brain. This is not physical. But, I mean, there is no linear system, right? Also here are some non-linearities. And it just happens that in this case, the difference, so F2 minus F1, 3 minus 2 is 1. So it corresponds exactly to this F0. So the two effects are kind of also overlapping, which makes it stronger. And okay, of course, I'm saying again, the combination tone is really a brain effect, whereas the fundamental bass is a physical effect. And which part is which, of course, this is tricky to separate, but the two are actually collaborating together, which maybe is why the fifth is so important in music, because as soon as you get out of tune, all of those effects enter into play, and you feel the out of tune. And this is the tuning, the core of the tuning. All right, so summary of where we got so far. Wow, we are almost done. So we introduced quite a number of concepts, which is really like the basis for what we want to discuss in the entire series. And in particular, those are the important terms. But in particular, we have really this effect of the form of beatings in the waveform, and the fact that we have this sensitivity of the well-tuned versus mistuned symbol ratios. And so this means that we really observe this degree of consonance or dissonance, as Isabella explained before, which in first approximation looks correlated to the properties of the signal. Then, of course, there is a lot of cultural or subjective kind of component, because we are used to Western music, we are used to some kind of music or some other kind of music. So there is a component of this that is subjective, but there seems to be some component which is very objective, that is really physical, which means that then it's a totally legitimate question to say, can we actually formalize this concept? I can even come up with a test that measures this in a kind of objective way. And the answer, of course, is yes, and we are not the first one trying to do this. I mean, this has been done for years and years. We found traces from this guy Fodera from Palermo. I can say it because I'm from Palermo, so I was happy to see that this is a violinist that had a lot of spare time, probably also had a lot of money for that. So he engaged a team of violinists and asked them to hear several intervals to get and do this kind of measurement. What is consonant and what is dissonant? And there have been several tests over time until even very recently. So this is still kind of an ongoing work. So what do we want to do? Actually, we tried it also, but what we tried to do is with some variants, because what people did typically was always focusing on the octave, and also with the instruments, especially in the past, they had violins, they had pianos. Here we have the luxury of generating the sound the way we want, especially dropping the resonances of the instrument, so making it very kind of neutral, and so it's kind of easier for us. And for example, what we did indeed is that. So we generated a sound which is similar to what we heard so far, but even less like a plucked string. So it's something like this. So it's kind of metallic and very long, with lots of harmonics. And then we asked our colleagues to answer questions about, try to measure this, but on several of those ratios. Actually, we chose many of them. It was a long test. It was actually a bit painful maybe for some people, because we wanted to explore 2 octaves, not only one, to start with. And we also wanted to explore not only the 12 notes of the octave, because the question that we raised, why 12 notes? But why not? But why can't we go beyond? So let's go beyond. Let's try something else, and let's see what happens there. And so people were really asked to give a rank, a rank, more than a rank, really a degree of perceived consonance, so a value on a scale that goes from 1 to 5. So then we put really everything together, and we came up with this result. this is from 20 persons, then possibly this can be expanded. But already to have an idea, so how to read this, we have on the horizontal axis the ratio in logarithmic scale. So this is the unison, this is the octave, and this is the second octave. So this is 4 times the initial frequency. And the ratios, actually the numerical ratios are there. Then we also had to make it something, I mean, we could not really ask people to hear all possible ratios at all levels. So we selected a subset. So here we have a few more, and here a few less. But just to give you an idea of those values, what was given, we have, for example, this one is the octave. Then on the other extreme, this is, in musical terms, this is 3/4 of a tone. This you cannot even play in a piano, but it's a macrotonal sound. It's 3/4 of a tone. And then we have also a very well-known interval that is the major third, and also this one is actually what we call a tritone, so 3 tones, but on the second octave. Which goes, so you see a little bit high consonance in this direction, so the octave, the major third, and low consonance or high dissonance going to the bottom. So what's next? Well, now we have to interpret this, and especially can we come up with some model? So now I call again my colleague, because at this point the business is with her, and I want some theory to explain this. I'm done. Thanks for today, and see you tomorrow.
Thank you very much. I just take first questions from Zoom, if there are any. There's one in the chat asking for the Python notebooks to be available somewhere.
I would have expected that. Yes, they will be available. Some of them are already on my GitHub, but I will put some links.
Maybe so we can put the links on the lecture series, yes.
Yeah.
Are there other questions from the remote participants? No. Oh, wait. Yes. The presentation, yes, the recording will be available. There's a question on the recording. And are there questions in the room? You'll have to wait for me to hand you over the microphone.
I wanted to ask, excellent presentation. With the slide about the, like the implied bass, the Tartini tone, where you played a mistuned F0 frequency below the perfect fifth, was the F0 played just a sine wave, or did that have a harmonic series?
Just a sine wave. Very good question. Yes, indeed. If you were to add harmonics, then you have a real beatings. But no, it was just a sine wave, a pure sine wave to probe only that line, without any added harmonics.
Okay, that's fascinating. Thank you.
So yeah.
Any other? Yes.
So the sound that you played, they are coming at the same time. You see, when you are looking at this on the beating and all these patterns, what happens if you would have the sounds which are displaced in time? You mistune a little bit, and you, for example, at the frequency of 1 hertz, you see, you just mistune in the way which is just like when you play violin, you see.
Exactly. And then, well, in that case, honestly, chapeau to whoever can feel the difference. Because at that point, then you have the discrimination Limen that plays. And there we have a resolution which is in the order of, at the level of 1000 Hertz, is in the order of 3-4 Hertz. So below 3-4 Hertz, there is no way to really feel the difference. I can feel the 1 Hertz because of the beating, but on separate sounds, and think about something super fast. I don't know, the flight of the bumblebee. Play whatever, it's impossible. It's really impossible to feel a single note that is mistuned at that point. It's just too fast, right?
Thank you.
Which makes actually life easier to the player also.
Other questions? Oh, let me quickly check if there's anything else.
On Zoom, yeah.
Yes, the slides will be available.
Yes. And then make sure to make at least some of those waves also available.
Thanks. The sound illustrations are really excellent. Have you played with simulating other types of instruments that are not harmonic, like timpani or other percussion instruments that are not? Their harmonics are not
an harmonic series, indeed.
Yeah.
Yeah. Thanks for the question. Yes, we tried that as well, at least to see a little bit how much this effect is important. We didn't really go very far, but at least we tried with like mistuning all of the harmonics, even in a random pattern. And I still wanted to try the exact series of the Bessel functions, which is actually our membrane vibrates, like a drum. And I have this in the plans, but I never managed to really get there and do the full, because it's a little bit more complex in terms of mathematics. But already by doing harmonics which are, so hypertones, let's call them more generically, hypertones that are not harmonics, non-multiple, it's quite funny what you get. The level of I mean, the pitch becomes very, very fading somehow. And it's a little bit the pitch I mean, the sound, even the generated sound looks like a bell at that point. So the bell is more or less, gives a little bit of a pitch, but it's very, very, I mean, it's not very precise. That's the thing. So yeah, this is very visible, in fact.
Any other questions? No? In that case, thank you again.
Hello.
Yes.
I have a question.
Go on.
Yes.
Sorry, hello, very interesting. I missed maybe the main argument. All the objective criteria is beatings, and then how does this explain, or will you explain it tomorrow, why some ratios were pleasant, or let's say harmonic or non-harmonic, consonant or dissonant? I think the only thing you showed objectively that you can measure is amplitude, beatings in the amplitude. Is there another criteria that I missed?
No, indeed. So, okay, first to answer the first question is, so tomorrow we are going to see in details how to explain, how to model consonance and dissonance.
Okay.
The criteria, indeed, so one is the beatings are really objective in the sense that you see them as features in the signal. The roughness is more psychoacoustic because you don't really measure it in a way, I mean, this again we will see tomorrow. You can define it, you have models of that, but it's not something that you can measure without some people that tells you, okay, it's rough, no, it's not rough. So it's true that let's say the two ingredients are the beatings and then the simple ratios. The fact that you have two numbers that are co-prime that are small. And by small, I mean any number below 7. So it's very precise. I mean, it's very objective there.
Right. And then probably we will discuss if this is natural or cultural or what, right?
Yeah, there will be some comments on that as well.
Yeah, okay.
Yes.
Yeah. Thanks.
Okay, now I can see the hands on Zoom. There's no other hands. Not in the room, so we can thank again Isabella and Giuseppe and see you tomorrow.
See you tomorrow.